Okay, so let's start now. So before discussing the weekly assignments, I will ask, do you have any doubts from this entanglement EPR paradox thing that I told last week? If not, then just okay. I just want to finish this EPR paradox and entanglement few more, like the hidden variables one. Then we will discuss the assignment questions and related question regarding that. Okay. So last week I told what entanglement actually means, right? So you need simultaneous correlation into conjugate basis and also inseparability of two particle wave function state into individual particle state, right? As we give the example, like you need correlation in case of polarization entanglement, you need perfect correlation in HV as well as plus 45 minus 45 degree, these two conjugate bases, and also you shouldn't able to write it as a single particle state, right? Inseparability of two particle state. So these two conditions you need to satisfy. We call this as entanglement in polarization basis. Similarly, you can have entanglement in time, energy, or position, momentum, everything, right? You have like you need just two conjugate bases. Here the two conjugate bases are HV and plus 45 minus 45 degree, right? Hmm. Here two conjugate bases. Sorry. Conjugate bases here are H and V, HV and 45 minus 45 degree. These two are, this is one basis, this is another. These two are conjugate bases. And so with these two conjugate bases, you can have polarization entanglement. Similarly, if you have conjugate bases, like some other example of conjugate bases, do you have any other example of conjugate bases? Some other example will be position and momentum, right? These two are also conjugate bases. So in this case, you will have entanglement in position momentum. Entanglement in position momentum. Another example of conjugate basis is time energy, right? So you can have time basis and energy basis also. E is energy here. And then you have entanglement in time energy. And so you can have very many different kind of entanglement, right? So position, momentum, time, energy, these are continuous variable, right? Position, momentum, these are all continuous variable. So here you have entanglement, position, momentum, entanglement, time, energy. But you can have entanglement in discrete basis also, like HP plus 45 minus 45. These are discrete basis, right? Another example of discrete basis will be like angle and orbital angular momentum, right? This angle phi and orbital angular momentum L. These two are also conjugate basis, but these two are discrete. Like L can have value 0, 1, 2, etc. Phi is also discrete angle, right? So these are discrete. So here you have also entanglement in angle and orbital angular momentum. Okay. So EPR, what EPR told? EPR told that EPR asked this question, right? That I told next week, right? Sorry, previous week. That EPR asked, is quantum mechanics is complete, or do you need some hidden variable to explain this entanglement phenomena, right? So EPR proposed that you need some hidden variable things to explain quantum mechanics, right? Now check whether hidden variable can explain this or not. Okay. So EPR asked that, like, do we need some hidden variable to explain this entanglement phenomena? Okay. So EPR asks this question: do we need entanglement or not? Let's go to next page. So let's build an experimental setup. Okay. Let's build one experimental setup and see which one is correct. Quantum mechanics is correct or hidden variable is correct. Right. So the experiment is something simple experiment, that's like, so first one is you have some source of entanglement photon. Okay. So from here two photons are coming. These two are entangled. Okay. This is photon 1 and photon 2. These two are entangled. Okay. And you have a detector here. Let's start a detector like this. This is your D1 detector and this is your D2 detector. Okay. This is quantum entanglement, right? You have sources of entanglement photons, right? This is quantum mechanics. And as EPR told that you need some hidden variable, right? So EPR don't believe in these sources of entanglement photons, like, because they are asked the question that whether they exist or not, right? So EPR don't believe there exists a entanglement photon source. Okay, so what they did, they took two different sources. Okay, so this is first source 1, and this is another source 2. Okay, and they told there are some variables that are hidden. Okay, that's why it is called hidden variable. So they told there may be some hidden variables. So this is some hidden variables. So there are some hidden variables between the source 1 and source 2. Okay, so source 1 emits the first photon and source 2 emits the second photon. Okay, and there can be infinite number of rules. You can choose the rules between how source 1 and source 2 will emit the photons, because these are all hidden, right? You don't know, so everything is in your hand, so you can choose whatever variable you want, right? So there are several rules. These rules you can choose. Okay, there are several rules how these sources operate. Okay, so how this source 1 and source 2 will operate, that is in your hand. Okay, so you can choose any rules you want. Okay, and these two source is emitting two photons. Okay, now check the measurement. Now do the measurement. Here also you have detector 1, D1. Here also you have another detector D2. Okay, now let's do the measurement. Okay, so measurement 1. So you do the first measurement. Okay, so the first measurement, you see that if the first photon is horizontally polarized, if the first photon is H means horizontal polarized photon. Okay, if the first photon is H, second photon is also H. Measurement, this is measurement. Okay, so after measurement you are seeing this. After measurement, what you are seeing? You are seeing that if the first photon is H, second photon is also H. If the first photon is V, second photon is also V. So these are your measurement results. Okay, from the first measurement. So measurement 1 outcomes. So this is your measurement 1 outcomes. Okay, so measurement 1 outcome is if the first photon is H, second photon is H. If the first photon is V, second photon is V. Now, can you explain these measurement outcomes with hidden variables and with quantum mechanics? So we need to explain, right, these measurement outcomes. Can you explain these measurement outcomes? Can you explain these measurement outcomes? So how quantum mechanics will explain this? Can you measurement these measurement outcomes with quantum mechanics? So quantum mechanically, can you explain these outcomes? How will you explain these outcomes quantum mechanically? Quantum mechanically, you will say that this source of entanglement photon has a wave function. You will say that this entangled photon source has a wave function of the form psi is equals to, so this is psi state, right? So this psi is equals to, what will be the psi? So first one is horizontal polarized, right? This first photon is horizontal. If the first is horizontal, second is also horizontal, right? The second is also horizontal. And if the first is vertical, second one is also vertical. So if you can write the state of the source like this in this psi form, then quantum mechanically you can explain the measurement outcomes, right? So this will explain the outcomes. Now with hidden variable, can we explain the outcomes? With hidden variable, can you explain this measurement outcomes with hidden variables? So with hidden variables, you have to check whether you can explain it or not. Okay. So you have to fix the rules. So the rules you set between the sources, like, so you say that both photon will emit simultaneously. Source 1 and source 2 will emit simultaneously. It can emit simultaneously, right? It is not that surprising. Okay. So both sources emit simultaneously and same polarization. Okay. So this is your rule 1. So you can set any rules, right? Hidden variables, you don't need one hidden variable or two hidden, you can have many, right? So hidden variable means some conditions. Okay. So first condition is both source emit simultaneously and same polarization. Okay. So if first photon emits at t equals to 0, if first photon emits h, second source will also emit h, like this. Okay. Second rule, you said that 50% time both the sources emit h. Okay. And 50% of time both the sources emit v. Now if you set the rules between the two sources like this, like both sources emit simultaneously and same polarization, and 50% of time they will emit h and 50% of time they will emit v. So these two rules, these two hidden variables can explain your result, right? Nothing wrong. You can get this measurement outcome if you set the sources like this. Okay. If you set so both sources emit simultaneously and same polarization, and also 50% of time they will emit h, 50% of time they will emit v, then also your measurement outcome will be same like this what you got in experiment. Okay. So of course hidden variable can explain, right? So there is no problem with hidden variables, but so that's why so we can explain measurement outcome with hidden variables. Okay, these two are hidden variables here. Okay, hidden variables. So we may not need wave function or quantum mechanics. We may not need quantum mechanics for to explain these measurement outcomes, right? And well, why 50%? Because like the rules are in your hand. So these rules you can set. So you have to set the rules such that you can explain. Like you first do the experiment, okay? Then you try to explain the outcomes. So like whenever you are measuring H, first one is H, second one is also H. And whenever it is V, second one is also V, right? If you don't set 50%, suppose you said 90% of the time both sources will emit H and 10% of time they will emit V. Like then the ratio, like I think I should write 1 by root 2 factor here. Like this probability should be equal, like that thing. Understand? I mean HH probability I'm getting HH is equal to probability of getting VV. That's why I nothing. So you don't need quantum mechanics to explain these measurement outcomes, okay? As EPR told, okay? So EPR is fine up to this, okay? But the question is this entanglement? So with this only one measurement, can you say that this state is entanglement or this measurement is entanglement? Like is this measurement or is this experiment measurement outcome of this experiment is entanglement? Can you say this is entanglement with only one measurement? This is not entanglement, right? Why? Because these are perfect correlation, but this is only H and V basis, right? Correlation in one HV basis only. For entanglement, what you need? You need correlation in both bases, right? As HV and plus 45 minus 45, right? So only this measurement will not tell that this is entanglement or not, right? But of course, you can explain this outcome with hidden variables. There is nothing wrong. You can explain this with quantum mechanics also, with hidden variable also. Okay. Let's do another measurement. Okay. Now measurement 2. Measurement 2 outcomes. So in another measurement, what you are getting, suppose you do another experiment in the same setup and you got the outcome like this. Now your outcome is if first photon is 45-degree polarized, second photon is also plus 45-degree polarized. And if the first photon is minus 45-degree polarized, second photon is also minus 45-degree polarized. Okay. Now this is your measurement 2 outcomes. Now again you want to explain these outcomes. So first you try to explain with quantum mechanics. So with the help of quantum mechanics, can you explain the outcomes? Of course you can, right? If you write the source, this source wave function psi like this only. Suppose you write the source wave function psi like 1 by root 2, 45, 1 minus 45, sorry, this is also 45. Second one is also 45 plus minus 45, 1 minus 45, 2. So if you write the wave function of your source like this psi form, then you can explain this your experiment outcome. Now with hidden variables, can you explain? With hidden variables also you can explain these outcomes. Okay. Now you have to change the rules just slightly. Instead of h, you just put v. Okay. So first rule, first hidden variable is same. Okay. Both emit simultaneously. Both emit simultaneously. Okay, both emit simultaneously and same polarization. And second hidden variable you set like 50% of time both emit plus 45 degree and 50% of time both emit minus 45 degree. These two hidden variable you can explain the measurement outcomes like so same thing we can explain this measurement outcomes with hidden variables. Okay, the same valid here also. Okay, same valid. We don't need quantum mechanics. Okay, but is this entanglement? The question is this entanglement? Here also you cannot say it is entanglement. Okay, why? Because here only 45 minus 45 degree polarization. Okay, here you are seeing correlation in 45 and minus 45 degree basis only. Previous outcome it was correlation only in HV basis only, one basis, that is HV, right? Second one, this is also one basis, only 45 minus 45 degrees. This is also not entanglement. Okay, why? Because entanglement, again I am saying this is very important, entanglement needs correlation in both bases. Okay, not only that, you can inseparability is fine. Okay, for mathematical, if your state is inseparable, mathematically you can say this is entanglement, but physically, like, you need correlation in both bases. Okay, so first one you cannot say entanglement, second measurement you also cannot say entanglement. Now the final experiment, now you need entanglement in, need correlation in both bases. Okay, now this is the final measurement. Okay, now you measuring h and 45 both. Okay, measurement 3 or final measurement. Okay, you see your final experiment, measurement 3 outcomes. Now measurement 3 outcomes, you are seeing that if first photon is h second is h. If first photon is v, second is also v. Okay, this is your measurement 1, similar, right? If your first but the thing is measurement 3 is if your first is h, second is also h. If your first is v, second is also v. But there is an and if first photon is plus 45 degree, second is plus 45 degree, and if first photon is minus 45 degree, second is also minus 45 degree. So in measurement 3, what you did, you combine the two measurement outcomes of measurement 1 and measurement 2, right? This is your outcomes of measurement 1, this is your outcomes of measurement 2. And measurement 3, or in experiment 3, what you are seeing that if the first photon is h, second is h. If the first one is v, second is also v. And this and is important, okay? You are not stopping here. If you measure the first photon is 45, second one is 45. If you measure first one is minus 45, second one is minus 45. So this is your measurement outcomes of experiment 3. Okay. Previous cases this and was not there. This is was separate, this is was also separate. Now in measurement experiment 3, you are seeing these two results at the same time. Okay. Now quantum mechanics. Can you explain these outcomes now with quantum mechanics? Can you explain this outcome with quantum mechanics? Can you explain these measurement outcomes with quantum mechanics? Can you write one wave function of the source? This you have this quantum mechanically you have this source of entanglement photon. So what will be the psi? Is there exist any psi that you have to see? If you cannot write any psi, then quantum mechanics is not valid, right? But if you can write any psi, then quantum mechanics is correct. Because this is your final one, because here you are measuring in both bases also, right? This is HV basis and this is 45 minus 45, both bases. Now you are measuring in both bases, right? So so certainly there is now entanglement, okay? If entanglement exists. So what will be the psi? Psi will be just first one is H, second one is also H, is 1 by root 2 is there. If first one is V, second one is also V. And this is equal to this. This equal to is important, right? This equal to 1 by root 2, 45 1, 45 2. If the first one is minus 45, second one is also minus 45. Okay, so this, if you write psi like this, psi this equals to this, then you can explain the results, right? But now the question is hidden variable, right? Hidden variable, can hidden variable explain? Now you set your rules. Can you set, previous experiment you set two hidden variables, both emit simultaneously, same polarization, 50% time plus 45, 50% of time minus 45. you can have as many hidden variables you want, you put, but you cannot explain. Okay, like how many rules you can try, right? You will see that you cannot. Okay, you can try as many rules, 3, 4, 5, doesn't matter. How many rules you make, but you will like 1, 2, 3, don't know how many you make. Okay, but you will never be able to explain these results of experiment 3. Okay. So experiment 3 result, this outcome. So experiment 3 outcomes only quantum mechanics can explain, not hidden variables. Okay. So as EPR told, there can be any hidden variables, so that is not correct. Okay. Quantum mechanics is all that is correct. Okay. Because in physics, that is where it is done, right? If you can show one experiment that if you can find one experiment that Newton's law is not valid, then whole Newton law is invalid, right? So that's this one experiment just tells you that quantum mechanics is correct, hidden variables is not correct. Okay. You can try as many rules you want, but you will not be able to explain. But this wave function, if you write psi in this form, right, is same as previously, right? You just equal the two wave function, right? This equal sign is important. This equal and this and. Why you can write, because h you can write 1 by root 2 like plus 45 minus 45. If you just break, you will get this. Okay. So that's why quantum mechanics is correct, hidden variable is not correct. Later then comes Bell's equality. Okay. Test of quantum entanglement. Sorry, Bell's inequality. Later people set up many experiments and they showed that Bell's inequality. Right? There, I think in class you already read that Bell's equality value. But the basic thing is that hidden variable is not correct. Just by do this experiment, you can say that hidden variable is not correct. Do you have any questions regarding this hidden variable thing? Not okay, fine. I will not. I'll not discuss this Bell's equality. You can just see many experiments are there, Bell's equality. Okay, let's tell something about quantum measurement. I will solve the assignments after 8, I think. Okay, just finish this first three things. So quantum measurement, suppose there are some important thing about quantum that I want to tell. Okay, whenever you do measurement, right, there is some measurement device, right? You measure something with some device is there. Suppose you measure voltage with you have multimeter or something. Right? In quantum mechanics also you have some device, right? What are the devices you have? Like, suppose this is your wave function psi and you are measuring the polarization. Okay. So in this case, what is your measurement device? So suppose like first one, suppose you are measuring the polarization of light. So in this case, what will be your measurement device? So there is your some sources. Source has some wave function. This is your source which has wave function psi. Okay. From here your field is coming and you are detecting here, measuring and detector. So here is some device, right? Measuring device. And this is your detector. Here you are measuring in the detector, right? And from source some light is coming and you are measuring polarization in the detector. Yeah. So here you can say the measuring device. You can have many kind of measuring devices. One example is polarizing beam splitter or polarimeter, whatever you want. Okay. So you put on PBS, polarizing beam splitter. There can be many, right? So I just put one PBS. So what PBS will do? PBS will send, suppose the here in this direction they will send a vertical polarization and in the up direction you will have horizontal polarized light. Okay, and you will be detecting here. Okay, so here the measuring device is a beam splitter. Okay, so here in HV polarization basis, your measurement device is a beam splitter. Okay, so this beam splitter splits the field based on whether it is horizontally polarized or vertically polarized, right? So that's why we told whenever there is a measurement depends on the basis. That's why, okay. So in words, if you want to write, we write like measurement in a basis is always associated with a device, okay. Measurement in a basis is always associated with a measurement device, okay. Here in the HV basis, you are measuring polarization in the HV polarization basis, and in this HV polarization basis, your measurement device is polarizing beam splitter, okay. Now the same setup, you just change the basis, okay. Instead of HV basis, you now measuring in the plus 45 minus 45 degree polarization basis. Same setup, but now you are measuring in a different basis. I'm just telling why basis is important, like in a different basis. You have the same setup. You have the source which has wave function psi, and you have some measuring device, and you are detecting, this is your detector, okay. So this detector will tell you whether it is horizontal, vertical in the first case, okay. Now that in the detector you are measuring in plus 45 degree minus 45 degree basis, okay. So now your polarization basis is 45 minus 45 degree, not HV. In the first case you are measuring in the HV polarization basis, right? But in the second case the setup is same, okay, experimental setup is same, but now you are measuring in plus 45 degree minus 45 degree polarization basis, okay. So you now want to measure, so you need some device that will give here suppose plus 45, in the upper one it may give you minus 45 degree, okay. So can you use the same device, this polarizing beam splitter? You cannot use the same one, okay, because this PBS will give you vertical here and horizontal in the up, right. Now if you send plus 45 degree photon, suppose if you want to measure plus 45, so this device you can make some arrangements like, but the probability will not be same, right? So the device you just change to, you keep the beam splitter same, but it is not horizontal basis, like same PBS but in plus 45 degree minus 45 degree, okay. So this is a kind of PBS that will split in plus 45 degree minus 45 degree basis, okay. The first one is also a PBS polarizing beam splitter that will split H and V like this, and this PBS will split plus 45 degree minus 45 degree like this. So this PBS, you can have many different kind of PBS, okay. So first you can have PBS which can split HV, you can have PBS which can split like this 45 minus 45 degree. So in the first case you will use this type of PBS, in the second case you will use this type of PBS, okay. Because now you want to detect plus 45 degree minus 45 degree polarization. So that's why I told measurement in a basis is always associated with a device. Okay. First you decide what what basis you want to measure. Okay. Then you take the device according to your measurement. Okay. First you fix your measurement. When you start the experiment, first you fix that I want to measure this. When you fix that I want to measure this, then check your measurement is in which basis, HV or plus 45 minus 48. If your measurement is in HV, then choose the beam splitter 1. And if your measurement is in second, like 45 minus 45 degree, you choose the beam splitter 2. That's how you do the experiment. Okay. In quantum mechanics, you can have some other base. Suppose every in lab, what we use CCD camera, right? CCD camera is also a measurement device. It is also a, or any camera, it is also a measurement device, but in position basis, right? Position basis, because in CCD what you have some pixels, right? So these are nothing but position. Each pixel can be some micrometer. Okay, suppose this is one pixel, 1 2 3 4. So these are all pixels, and each pixels can be some micrometer range, or maybe smaller than this also. Okay, and if the photon hits this first pixel, you can know its position, right, from some image processing, whether the photon hits here or hits here or hits here, hits here. So ultimately with CCD, or what you are measuring the position of the photon, right? How measurement device and detectors are differentiated? Not that much difference, I will say. Like CCD here is a detector, right? So it depends how you want to use the device. Okay, as a detector or as a measurement device, right? There is not that much difference, I will say. Okay, the CCD camera you can, as a, like, it is a detector actually, right? CCD camera, it is a detector. So it's, you can say detector is another kind of measurement device also, right? So both are like same kind of. Now suppose, so as I was telling, so CCD camera you measure position, right? It's a, it's a detector or measurement device, whatever you want to call, doesn't matter. So the main thing is, when you are using CCD detector or measurement device, your basis is position. You are not measuring polarization. Like when you want to measure polarization, you use PBS or some other detectors or something, right? So that's the main thing. Okay. When you are using CCD, you are measuring position of the photon or something that is falling on the detector or CCD. Now you want to measure the momentum of the photon. What you will do? You will use CCD. You will not use CCD. Will you use polarization beam splitter? You will not. So you need some different device, right? As you change the basis, in position basis you are using CCD. In momentum basis, what you will use? Suppose now we want to measure momentum. Now you want to measure the momentum. So now your basis is momentum basis, right? So what you will do now? Use your momentum basis. How will you measure momentum? And what device or what detector you want to use now? Position you can easily measure with the camera, right? Photoelectric. How photoelectric? Photoelectric how you will do? I don't know. You just use one CCD camera. You keep one CCD, okay? Same CCD camera as you use. You don't need to change many things, okay? CCD measure position, understand, okay? But you know that how to convert the position to momentum, right? These are conjugate basis. I think I don't know you know or not. You just put a lens. What lens do? Lens do the Fourier transformation. Okay. You just put the CCD camera on the focal plane of the lens. Okay. Just make sure this distance is f. This is your lens, and whatever suppose these photons are coming, it will just Fourier transform. Like x, it will convert to p in the Fourier plane, like in the CCD camera. Now the positions you are measuring, now we will measure momentum at the same pixels. Okay. Suppose in pixel 1 you are measuring position. Now in pixel 1 you will measure momentum because you now put a lens and lens to the Fourier transform. Okay. You can derive, okay. You can just search in the Google, you will know that how lens to the Fourier transformation, okay. Lens to the Fourier transformation. So just put a lens and it will you get the momentum, okay. So this is your measurement device now. Lens plus CCD. In this case, when you want to measure momentum, now your measurement device is lens plus CCD. If you want to measure position, your measurement device is only CCD. But in momentum, your measurement device is lens plus CCD. Sorry, CCD at focal plane. It is important, okay? Lens to the Fourier transformation at its focal plane, okay? So at f distance, you put the CCD. Okay? So this is in momentum basis. So in momentum basis, your device is this. In position basis, your device is this. In plus 45 minus 45, your device is PBS plus 45 minus 45. In HB, your device is this. So the measurement, so that's why I was telling again, the measurement will decide which device or detector you will use. Okay. So first, make sure what you want to measure. Okay, fine. Okay, I will tell many things. I have something. Next class, I will tell some theory about communication, all these things. Okay, let's just first solve the assignments and related problems first. If I get time, I will tell today or not. Otherwise, next week. Okay. There are some like quantum transportation, all these things I want to say. Next week, I will surely say. Okay. Okay. First one is I think already done in the class. Like this is incorrect, right? Projector operator, you need PM square equals to PM, right? So that is fine. Second one, entanglement, right? Second one is also just already done in the class, right? Entanglement states created by application unitary operations, right? Second one is also I'm not doing. First and second is also done, right? If you don't understand, you ask. So I will start the third one, okay? Okay, before starting, I just want to say regarding the entropy one. Uh, So entropy, like as I told in the class, right? You can classically write S equals to kb ln omega. Omega is the number of microstates, right? These things you can like minus kb sum over I pi ln pi. Now, in the context of information theory, right? In the context of information theory, what Shannon told, Shannon in 1948 told that you can write entropy like this minus sum over x px log px, right? Probability of outcome associated with x. Px is nothing but probability of outcome associated with x, right? Now, why we are interested in measuring S, like entropy, like mm, just okay, fine. So, what S does? It is a measure of uncertainty content in a system, right? So, I am not discussing the theory, all these things now. Then, in quantum mechanics, Newman comes and tell that you can write S as a rho because in quantum mechanics everything is in terms of density matrix, right? So you can write S rho like minus sum over I pi log pi, that you can write like sum over minus lambda I log 2 base lambda, right? So this is the formula we need. So let's start the first problem, okay? So consider a mixed state consisting of plus with probability 1 by 4 and minus with probability 3 by 4, and we have to calculate the entropy for the mixed state, okay? So you have plus state is given by 1 by root 2 0 plus 1, right? And minus state minus state is given by 1 by root 2, 0, minus 1. These are your two states, okay? Now you note that 0 means 1 0 and 1 means 0 1, right? So the plus state you can write like 1 by root 2 1 1, right? And minus state you can write 1 by root 2, this will be 1 minus 1, right? This is plus and this is minus. Now you want to write the density matrix, okay? Because you need this lambda I, right? Lambda is nothing but the eigenvalues of your density matrix. So rho, you first write the density matrix of your mixed state. Now what they told that consisting of a mixture of plus state with probability 1 by 4 and minus state with probability 3 by 4, right? So in the mixture you have plus with probability 1 by 4. So this is for the plus and minus with probability 3 by 4. So this is for the minus, right? So this is your density matrix of your mixture. Density matrix of the mixture. Fine. Now what will be these things? 1 by 4. This is 1 by root 2. 1 by root 2. 1 1 1 1, right? Plus 3 by 4. 1 by root 2. 1 by root 2. 1 minus 1. This is also 1 minus 1. Now you do these things, you will what you will get. This is 1 by 8. This is 1. Like this is 1. This is 1. This is 1, right? Plus 3 by 8. This is 1. This is 1. This is minus 1, right? And this is minus 1. This is plus 1. Fine. Just do the multiplication. Then you will get, this will be, you just do, you will get 1 by 4. This will be 3 by 8 and 1 by 8, 4 by 8, right? So this is 2. 2 minus 1 minus 1, 2. Right? So this will be your density matrix of the mixture. Now for the lambda I, you have to calculate the entropy, right? So you need to calculate the eigenvalues. Eigenvalues of rho. So what will be the eigenvalues? So determinant of 2 minus lambda minus 1 minus 1, 2 minus lambda equals to 0, right? This will be 2 minus lambda square minus 1 equals to 0. Something is wrong in doing it. This is 4 factor is there, right? I'm missing this. Sorry. this you write 1 by 2 minus 1 by 4 minus 1 by 4 1 by 2. The determinant of 2 minus lambda minus 1 by 4. Now if you solve, you will get like lambda equals to 1 by 4 and 3 by 4. Okay, so your S row will be given by minus sum over I lambda I log 2 base lambda I, right? This is minus lambda 1 log 2 base lambda 1 minus lambda 2 log 2 base lambda 2. Okay. So just put lambda 1 is minus 1 by 4 log 2 base 1 by 4 minus 3 by 4 log 2 base 3 by 4. Just put the minus sign inside log, so you get 1 by 4 log 2 base 4 plus 3 by 4 log 2 base 4 by 3, right? This will just change the sign inside log. Now log 2 base 2 square, right? Plus 3 by 4 log a by b means log a minus log b, right? Log 2 base 4 minus log 2 base 3. So first term will give you log 2 base 2 square. So these 2 will come outside. So we will get 2 by 4 log 2 base 2 plus 3 by 4 into same thing 2 log 2 base 2 minus log 2 base 3. Right? So this is nothing but 1 by half. Now log 2 base 2 is 1, right? So this term will give half plus this is also 1 log 2 base 2. This term will give you 3 by 2 and minus 3 by 4 log 2 base 3. So this will give you 2 minus 3 by 4 log 2 base 3. Okay, and if you just calculate this term only, you will get 0.81. Okay. So this is 0.81. So this is the entropy of your mixed state. Okay. I just want to do another similar thing, but I just want to discuss one interesting problem, like same but little bit different. Suppose you have two particles like A and B, right? Suppose you have two qubits A and B. Two qubits A and B means A can be 0, 1 and B can also be 0 or 1. Right? Now you are given the 2-qubit state like this, and you are given the 2-qubit state, sorry, 2-qubit, whatever you write the 2-qubit state, psi is equals to okay, psi is equals to right plus, and you are given the 2-qubit state psi is equals to cos theta 0 0 plus sin theta 1 1. Okay, this is your 2-qubit state psi. Now this is a mixed state, right? Because there is no information about whether it is cos theta or sin theta, right? There is no information about cos theta sin theta. Now you have to say these two particle state like A and B. Now comment on entropy of the, suppose, SAP, like entropy of the mixed state. Okay, SAB, and it is the entropy of the mixed state, this mixture. Okay, this psi, and the individual state SA, SB, entropy of the individual subsystems A and B. With A and B, you got this mixed states AB, right? AB has the state psi. Now we have to calculate just entropy of the SAB, the mixture, and the individual states also. Okay. So you are given the two particle state psi. So first you calculate SAB. Okay. So to calculate SAB, what you need? You need rho AB, right? So we calculate first rho AB. This is the density matrix of the two particle state. So rho AB will be given by psi psi. So if you do this, what you will get? Psi psi will be, this is cos square theta, this is 0 0 0 0, right? Plus sin square theta 1 1 1 1 plus cos theta sin theta, you will get this 0 0 1 1 plus 1 1 0 0. Okay. This is your row AB. Okay. Now you calculate row A. You have to take the partial trace then, right? So row A means what? Trace of B, row AB, right? This is the formula partial trace, you know. So you calculate row A. What will be row A? So row A means you keep your A means first one. This is A, right? And second one is B. So we keep the first one fixed. Trace over B means inner product of this 0 with this 0, right? So first term you will get 0 0 cos square theta 0 0, right? From the second term what you will get? First you are taking trace over B, right? So this and this will be inner product. So 1 1 and other will be same, sin square theta. First you remain same, first term. From the second one what you will get? This is cos theta sin theta. This will be 1 0 inner product. This is 0, this is 1 plus 0 1 inner product 1 0, right? Just calculate, you will get this. Okay, so this is your partial trace. This is your row A, density matrix of the subsystem A. And what the row A? So these terms are 0, right? This is also 0. So you, and this is 1, right? So you are left with row A is cos square theta 0 0 plus sin square theta 1 1. To write in a matrix form, in matrix form you can write cos square theta 0 0 sin square theta, right? Is 0 0 0 1 1 0 1 1. The coefficient is there. So 0 0 term has coefficient cos square theta, so cos square theta. 0 1 term has no coefficient, so 0 1 0 is same, and 1 1 term has coefficient sin square theta. So this is your row A. Now the entropies of the two components A. So similarly you can first, okay fine, entropy of the component A. Entropy of A you can calculate is A. SA will be what? Minus sum over I lambda I log 2 base lambda I, right? And lambda I is the eigenvalues of row A. Now what is the eigenvalues of row A? It is diagonal matrix, right? So eigenvalues are nothing but cos square theta and sin square theta, right? So it has eigenvalues. Lambda 1 is cos square theta and lambda 2 is sin square theta. Okay, these two are the eigenvalues. Very simple. So entropy of your component system A is given by this. So minus lambda 1 log 2 base lambda 1 minus lambda 2 log 2 base lambda 2, right? this minus cos square theta log 2 base cos square theta minus sin square theta log 2 base sin square theta. So this is minus 2 cos square theta log 2 base cos theta minus 2 sin square theta log 2 base sin theta. Okay, so this is your SA. Okay, similarly you just try, you will get that SB. I'm just writing the result, you just do yourself. Okay, similarly you will get, you just now take the trace over A. Okay, partial trace, you will get SB. SB you will get like this, minus 2 cos square theta log 2 base cos theta minus 2 sin square theta log 2 base sin theta. Same. Okay, log 2 base sin theta, same at SA. Okay, so now if we want to, now you sum SA and SB. Okay, now let's, okay, similarly you can calculate the SAB also. You know row AB, right? You know the row AB term, and from there you calculate the SAB. Okay, SAB is, you will get 0. Okay, you just check these two things, you do yourself. Okay, I'm not doing because I don't have much time. So SB you will get like this, just similar to what I did here. Okay, in case of A, SB you will get this, and SAB you will get 0. Okay, now do the summation. Okay, SA plus SB. If you do SA plus SB, what you will get? You will get minus 4 cos square theta log 2 base cos theta plus sin square theta log 2 base sin theta. Okay, now just tell me whether this SA plus SB is greater than 0 or less than 0. I mean, SA plus SB is positive or negative, this whole term. So calculate SAB. SAB, you have this row AB, right? You just need to find the, you have to write the density matrix, you know, write it in the matrix form. Okay, and then find the eigenvalues in matrix. This is 0 0 0 1 1 0 1 1 0 0 0 1 1 0 1 1, right? So first term is cos square theta, 1 1 1 1 is sin square theta. Okay, and this 0 0 1 0, right? 0 0 1 0, right? So this is cos theta sin theta, and 1 1 0 0, this is cos theta sin theta, other side 0. Okay, you have this 4 by 4 matrix. Okay, from here you can calculate the lambda and you will get. Okay. Okay. So this SA plus SB, will it be greater than 0 or less than 0? So for this you have to check, right? Now check whether cos theta is always less than 1, right? Not always. I mean, cos theta is less than 1 except cos 0. That thing, and sin theta is less than 1, right? So this term is less than equals to 1, and this term is also less than equals to 1, right? Now you are taking the logarithm of these terms, right? Then what will give, this is less than 1, so this term will be what? Greater than, sorry, this term is also negative, right? Taking logarithm of something less than 1, so you will get negative, right? This term is also negative, right? And this is negative, this is negative. Cos square theta is positive, sin square theta positive, and here is this minus 4, right? So this negative and this negative will make everything positive, right? So SA plus SB, you will get greater than 0. Okay, and as I told, you will get, you just check, you will get SAB equals to 0. Okay, that means what? SA plus SB, right? This is 0 and this is greater than 0, so you can say SAB is less than SA plus SB. Okay, so in general you can say that entropy of the mixed state is less than the sum of the, in mixed state means, I mean here mixture. Okay, entropy of the mixture is less than the sum of the entropies of the two component pure state. Okay, so now do the quantum circuit one, last one. Okay, this 4 number I will do. 5, 6, 7, 8 will be done tomorrow. Okay, so 4 is, this gate is there, right? What will be the output you need to know. So you have the circuit here, it is 1, it's going to some Hadamard gate, right? and second one is 0. It is going to another Haramat gate, right? And you have this. This is your control and this is your target, right? And then another header mark, then there is another header mark, and this is your output. So you have to tell what will be the output here, right? This is the thing, right? So you know this is the control qubit, right? This is your control qubit and this is your target qubit. And what you know, what this CNOT gate do? This is a CNOT gate, right? So if the control qubit is 1, then only the target will change its state, right? If the control qubit is 0, then target will remain same, right? And what the Hadamat gate do? So if you apply Hadamat on 0, what you will get? You will get plus state, right? Plus means 1 by root 2, 0 plus 1. And if you apply Hadamat on 1, what you get? You get minus state, right? This is 1 by root 2, 0 minus 1. And if you apply Hadamat on plus, similarly you can say you will get 0. And if you apply Hadamat on minus, you will get 1. Okay, and this is the CNOT gate. Just one example of CNOT I want to give just to be comfortable. CNOT, suppose you acting CNOT on root 3 by 2, 0, 0, 1 plus 1 by 2 is a 3 qubit gate, okay? 0, 1, 0. If you apply CNOT here and you are told that third is control, third qubit is the control and second qubit is the target, and what will be the output of this? You are told third is the control and second is the target, right? So if you want to draw a diagram, so third is the control and second is the target. So it is like this only. Okay. So if you apply C naught here, what will happen? First term will be root 3 by 2. Third is the control, right? So here third is control. Control is 1 here, right? If control is 1, then target will change its state, right? Target is second, so 0 will become 1. It is become 0, 1, 1 plus 1 by 2. Third is the control, right? Control is 0. So everything will remain same. 0, 1, 0. This is C naught gate, right? Now let's come here. So The best way is to define the states here, okay? Suppose this is your psi0 state. Here you define your psi1 state and just keep on writing psi0, psi1, psi2. And here this is your psi2 and outcome is your psi3 state. Okay. Now step by step. First is psi0. What is your psi0? First is 1, second is 0, right? Psi0 is 1, 0. You can write this as 1, 0. So this is your state psi2, the input state. This is your input. Okay. Now you apply Hadamard, apply H on first qubit and H on second qubit. Okay. This is your initial 2 qubit state. Now you apply Hadamard gate on first qubit. First qubit is in state 1 and also you apply Hadamard on second qubit which is in state 0. So this is your first qubit and this is your second qubit. And you apply Hadamard on first, also Hadamard on second. So now what will be your 2 qubit state? So input state, so this is a 2 qubit state, okay? So this psi0 is your input 2 qubit state. So after applying Hadamard, what will be your 2 qubit state psi1? You have to write the psi1 now because psi0 will become psi1 here, right? Here your 2 qubit state is psi1. So what will be your psi1? So what you did, you apply Hadamard on first qubit. So here you can see that first qubit is in state 1. So if you apply Hadamard on 1, what you will get? You will get minus state, right? So it will become minus and second one will become plus, right? You are applying Hadamard on 0. So it will become plus. So this is your psi1 minus plus. Okay. Now you write this in terms of 0, 1. So that will be better. So minus state is nothing but this will become 0 minus 1 and this is 0 plus 1. Okay. Wait. 0 plus 1. So this is your psi1. Okay. Now you write this half. So first term is 0, 0 minus 1, 0 plus 0, 1 minus 1, 1. So this is your psi1 state, right? This is your psi1. Now after psi1, what you did? Then there is a control qubit, sorry, C0 gate, right? Now you apply C0 gate on psi1. So now you apply C0 on psi1, right? Now you apply C0 gate on psi1. What will be your step? After applying C0 gate, your psi1 will become psi2 here. Here your state is psi2. So what will be your psi2? Now you are applying C0. So let's apply C0. Now C0, you see your control is the second qubit, right? Second qubit is your control qubit. First it's the target qubit, right? Second one, so this is your control and this is your target, first one. So second one is control, right? Second one is 0 here. So 0 means it will remain same as it is, 0 0. Minus second one again 0. So it will again remain same, 0 0 minus 1 0. Now check the third one. Here the second qubit is 1. So control is 1. So target will change state. So 0 will become 1. So it will become 1 1. Minus here also second control is 1. Second qubit is 1. Control is 1. So first target will change state from 1 to 0. This will become 0. This is 1. Right? So this is your state psi 2. Okay. You got your psi 2. Now what you do, you again hammer on both qubits, right? Now this is your psi 2. Now here what you do, you apply hammer on first qubit, you have also apply hammer on second qubit, right? So you apply hammer on first qubit, you also apply hammer on second qubit, right? Now what will happen? We will get state psi 3 here, right? After applying two hammers, the state here is psi 3 here, right? The 2 qubit state is psi 3 here. So what will be your 2 qubit state psi 3? First you apply hammer on both the qubits, right? So this is your half. Now keep on applying hammer. Now hammer get on 0, what will do? 0 will be plus and 1 will be minus state, right? 1 by root 2 0 1, 1 by root 2 0 minus 1. So first qubit you write 0 0, right? So first qubit is 0 0 will be plus, right? So this is your plus. So this state will be becomes plus. Second is 0 will become plus, right? Minus first qubit is 1, 1 will become minus and 0 will become plus. Plus first one is plus, so this will become minus. Second one is 1, so this will become minus. First one is 0, 0 will become plus. Second one is 1, 1 will become minus. So this is your psi 3. Now if you want to know psi 3 in terms of 0 1, just write plus and minus state in terms of 0 1. Okay, so you will get 1 by 2 outside 1 by 4. 1 by root 2, 1 by root 2, so 2 will come 1 by 2, so this will become 1 by 4. And inside what you will have, this is 0 plus 1, this is 0 plus 1 minus, this is 0 minus 1, this is 0 plus 1. Okay, plus this is 0 minus 1 into 0 minus 1, and last one is plus means 0 plus 1 into 0 minus 1. Okay, this is your psi 3. Now just break everything. Okay, so 1 by 4 you will get 0 0 plus 1 0 plus 0 1 plus 1 1 minus 0 0 minus 1 0 plus 1 0 minus 0 1 plus 1 1. Okay, here you will get 0 0 minus 1 0 minus 0 1 plus 1 1 minus 0 0 minus 1 0 plus 0 1 plus 1 1. Now check what are the things vanishing. Okay, 0 0 0 0 0 0 0 0. This is gone. Plus 1 0 minus 1 0 plus 0 1 minus 0 1 plus 1 0 minus 1 0 plus 0 1 minus 0 1. All are gone, right? Only 1 2 3 4 4 1 1 state is left, right? You will get 1 by 4 into 4 1 1. So this is 1 1. That means first qubit is 1, second qubit is also 1. So your measurement outcome will be 1 1, right? You will get 1 here and 1 here, right? So the outcome of your result side 3 is 1 1. The 2 qubit state is both qubit is in plus 1 state. Okay, next week most probably I will discuss about quantum cryptography and quantum communication. Okay, then Alice Bob, all those things. Okay, maybe the quantum key distribution little bit. Okay, so all those things is straight little bit I will just discuss. If you have any doubt, ask. Otherwise, I will end here. Okay. Okay, then thank you everyone. Next week, quantum key distribution and cryptography, all those things. Okay. Just read little bit. Okay. Okay. Bye.